Hi everybody, thank you for joining SimScale's latest webinar, this time focusing on pedestrian wind comfort. So this is a new analysis type for us. We've spent a little while now getting it ready and now it's out in the wild and we want to talk about why we built it, what it can do and how to use it. My name is John Wild. I'm VP of Customer Success here at SimScale. So I'm running essentially three teams now, so the pre-sales and post-sales teams as well as the product team. So really interested in what all of our customers are doing, where the company is headed in the future. I've got a lot of CFD experience as well, so I'm pretty interested and excited about what we're going to talk about today. I'm also joined by Richard. Would you like to introduce yourself?
Sure. Hey everyone, I'm Richard. I'm here product manager at SimScale. I have a background in mathematics, studied applied mathematics and started at SimScale 2013 as a software engineer, and currently I'm here a product manager in John's team, and I'm responsible also for this new analysis type that we're talking about today.
Cool. The really cool thing is I'm not that stupid, I don't think, and Richard is really the smart one in this room. So that's kind of interesting.
Thanks, John.
He's shaking his head. I think just a couple of slides about who we are and what we're trying to bring to the simulation market. So we just had our 7th birthday, actually last week. We now have offices gradually kind of moving across the globe. So we're based here, our headquarters are in Munich. And nearly everybody actually works here, but we also have offices in Boston and New York, plus a few remote employees. We're now just over 80 people. We have more than 100,000 users worldwide and hundreds of thousands of simulation projects now. A lot of these are actually public, actually probably the majority, right, I would think. And that's the cool thing with SimScale. So everything, well not everything, but unless you're really a customer of ours, when your projects are then totally private, everything will be totally public and everyone can learn from each other as part of a community. So we are a browser-based simulation tool, and I think looking at everybody on the list who is in the call knows who we are already, I think, but I'll give a very quick overview. So what we set out to do really is to try to democratize simulation and like free everybody essentially from the shackles of local and expensive hardware, and enable all of our users and all of our free community users too to be able to utilize simulation just through a browser and on the cloud. So you don't need any local kind of hardware to achieve or to run CFD or FEA or thermodynamics analyses. Feel free, by the way, as we go to type in questions. We will see them pop up, and if we can talk to them as we go, we will. We might also leave some to the end. Let's see how it goes. If they're difficult, I'll just ask Richard to help me. So today's application is to talk about our new analysis type, which is a multi-direction pedestrian wind comfort. And we set about doing this because we have a really nice new solver, a Lattice Boltzmann solver, which we'll talk about a little bit more in a second. And it's really fast and it's really capable of dealing with not particularly beautiful geometry and really also large scale. So we can run these kind of city-sized models, you know, with just at least a single direction in essentially minutes, you know, and capturing many minutes in real time. And what we decided to do is to go one step further, because a lot of the people we were talking to said, hey, this is great, but I need to do, you know, maybe 8 up to 36 directions. And I need to do some statistical calculations, which Richard will hopefully try and explain a little bit more, on all of this data to really understand, okay, looking at putting everything together, what is really happening, you know, in the city over a year. And are the pedestrians going to be comfortable? Do we have like safety concerns? And everyone's doing this already, but like one kind of direction at a time, probably not with the speed of the solver that we have, and then having to kind of post-process and do all of the statistical calculations in different softwares. So what we thought is actually we could do this really easily all in SimScale, and again, just all on the cloud. So, and we'll walk through how to do this. Now we can do it all in one place, so you can import your city and get pretty quickly to the pedestrian comfort results. The other thing we wanted to do is to try to enable a lot of, I guess, architects and engineers who are, and other many companies who are using often wind tunnel companies to basically do this kind of calculation for them. And I would say we're not trying to replace wind tunnels, but what we really want to do is to enable somebody to not have to wait for that long kind of time to get results back, to get an insight into whether their design is good or bad, but within a day easily to start to understand what is going to happen within the city, and optimize it before they kind of go to that final validation step. Anything you wish to add so far, Richard?
Nope, all fine.
Okay. Just sit there looking clever.
Yeah.
Good. So we're going to kind of break today into two sections. So what I'd like to do is to give an overview of the new analysis type first and what it can do and how to set a model up. And then we'll also kind of look at the results too. So as well as just explaining what it can do, we'll give, because it's so easy to use, also a tutorial so we can use this again, or you'll be able to use this again later to use this yourself. Use the new analysis type yourself. So firstly, I thought maybe it's important to mention what we're using. So we have a Lattice Boltzmann solver, and that applies actually to two of the different analysis types that you can use within SimScale. So actually, when you bring your geometry into the platform and you create an analysis, you'll see this window exactly pop up. And these are all of the different types of things that you can do with that geometry. And the two that are highlighted are using the new solver. So it's a particle-based meshless simulation. It runs, you can run small things if you wanted to, but generally we're running huge models, and it's only transient. It's incompressible and isothermal. We tend to run hundreds of millions of elements potentially, and it only runs on GPUs. And again, all on the cloud, so you don't need anything local. So although we do have these two different analysis types, we're actually focusing on the second one today. So it's still using the same solver, but this is built very specifically for wind comfort. And you'll see the interface is similar to what I think some of you would have seen before, but we've taken out anything that is not needed, and it's just focusing on really the things you need to run wind comfort. Okay, so what I'd like to do is just to walk through the simulation setup. So essentially there are 3 steps to go through. And in a second, Richard is going to take over, but just to give a quick explanation, there's 3 things. So the first thing we do is to define the region that we're interested in. The second thing is to define the wind rows. So we need to tell SimScale, what direction the wind comes from, and how strong it is. That's pretty much what I know. Then you can speak to the rest. And then we need to define, not true, but we need to define our pedestrian zones. So we then need to say to SimScale, okay, these are the areas I'm interested in. Please go ahead and give me the results. So I'm going to hand over to Richard for a few minutes, and he's going to talk to you in a little bit more detail about the setup.
Yeah. So I'm speaking now as I'm not completely useless sitting here. So that's great. Okay, so usually we start with a CAD model of potentially a whole city. And the first thing to do is define actually the region and around the building of interest where we want to get our pedestrian results in the end. So we give the center point usually in the center of the building of interest and have a radius around it where people would get influenced by the new building, usually around 200 to 500, 600 meters maximum, depending also on the height of the building. This is where we're usually interested in the pedestrian comfort. So with that, we're defining our focus area. We will have a higher resolution within this area, and also our pedestrian comfort results will be restricted to this area. In a sense, this is comparable to what you will have in a wind tunnel on the turntable, right? So this is basically the stuff that you model in the wind tunnel and rotate for your 36 or 16 wind directions. Another option or another thing to look at is the wind direction. As we are later putting in wind data, statistical data for this location over the whole year, we need to make sure that north and south and east and west and so on is aligned to what we have in the CAD model. So for this you can define the north angle accordingly so that this aligns well with the wind data that you upload later. So this is essentially the first step. Next, now as we defined our region and made sure we have set it correctly, we at the second part for the analysis, which is the wind statistics. We can upload at SimScale wind roses directly, and they represent usually the average wind speeds at this location over a period of time, usually a year, and the data is normally collected over 10, 20 or 30 years. And this data can directly be uploaded to SimScale, and soon we'll also have an automatic import way so that you don't need to use your own data, but we will provide you with the correct data at this location. Once the data is in, you can have a look, make sure that it's imported correctly. So this is a typical wind rose, color-coded. You have the individual velocity bucket, so you know from which direction the wind speed is blowing, how frequently, with the specific speeds. The next thing that is essentially very important is for the scale of the model that we're using, or in general for city scale model, it's very important to capture the atmospheric boundary layer that usual winds have in reality correctly. How to define the atmospheric boundary profile is specifically defined according to the different wind engineering standards. Currently at SimScale you have the ability to choose between two different wind engineering standards, either the Eurocode or the Australia-New Zealand standard. And according to these, we will then, for the CFD analysis, define the wind profiles for the atmospheric boundary layer. And one thing that is also coming there is you need to define this atmospheric boundary layer according to the terrain that you will have in the inlet direction. So, for example, you can imagine that the wind that blows over open sea has a different profile going up with the height compared to wind that's coming over a densely built city. And basically this is what you then define for each of the wind directions of your wind rose. Right? We can use from 4 to 36 different directions. How many you upload, this is the number of directions you have to define the terrain for. And the last step, now at this point, so the first two steps are done. At this point we have completely defined the whole simulation setup. We should be good to go. The final thing is to define where do we actually want to have the pedestrian comfort evaluated. Again, according to wherever you live and to which standard you apply, or to which city. Sometimes each city has its own wind code. The height, the pedestrian height at which the wind speeds are evaluated might differ. Might be anything from 1.5 to 2.5 meters. This is usually the range of pedestrian heights. And for this, you basically just add a pedestrian comfort map, and you have two options in SimScale. You can define the height, that is sure for any option, but the height can be either absolute to the ground, so the ground is basically defined by the region of interest. This is typically okay if you have a flat terrain or you have no terrain at all. But as soon as you bring a model to SimScale with the terrain, it becomes difficult, right? So there is not possible to just define a plane for the height of the pedestrians, right? Because wherever they stand on the terrain, they will have a different height. For this, we have the ground relative option. It's very simple. You select the surface from your model, and we will elevate the surface. You see it maybe here a little bit. We will elevate the surface accordingly to the height that you define. It might be a flat surface, then it's easy. That is, for example, useful for balconies, terraces, and so on. But it could also be a curved surface, terrain like a hill or whatever. You might be in San Francisco. They usually don't have a flat terrain. And this is usually the best approach to use to get the correct pedestrian height across your evaluation. And with this step, you're done with all the main setups, and we're good to fire off the simulation. Okay, good. So before we move to the results, maybe we add some theory or at least some background and what we're actually doing behind the scenes. It would be too easy to just skip this, so we're doing it. in the end, what we're interested in is getting at the local place where people sit, stand, walk, a quantitative measure how they will feel, how comfortable they will feel over a whole year, right? And this depends on the wind frequencies and the wind speeds locally, but usually we don't know how the speeds locally are, right? At pedestrian level, within middle of a city, we don't have this information. The only thing that we have is some meteorological weather station where we know the wind statistics over the whole year. And now we need to transpose this to the local site and to the local pedestrian level and get the statistics at this place, and then we can in the end compute from that the wind comfort criteria, right? And usually they just define some exceedance probabilities of wind speeds throughout the year. So one could be if the wind speed is lower than 5 meters per second for more than 95% of the year, then we think it's comfortable for short-term or long-term sitting, right? And this statistics we need to build. And there are two different parts for it. The one part is basically we go from the meteorological location up to the beginning basically of our wind tunnel, right? And for this, the terrain might change, and to take this into account, we need to do an exposure correction. So as you can imagine, if the wind goes from a very flat terrain that you usually have around the meteorological stations, might be at an airport, up to the beginning of the city or the part that you model, you have more obstructions on the terrain and the wind will slow down locally at the lower levels. And there, basically to take into account for this, we have an exposure correction. And then from that point onwards, so from the point where we reach the inlet of our wind tunnel domain up to the local pedestrian level, this is basically a second speed up factor that we're taking into account. And this is what we're getting actually from the Lattice Boltzmann solver, from the simulation that we're doing. And these two combined gives us the total amplification factor that we need to multiply our wind data with, that we got from the windrows, to get to the actual wind statistics around each point of our domain. And these factors, they vary for each point of the domain, so there's some calculation involved with this. So one other thing is that the wind data that we get is discrete. So we have seen that there are velocity buckets from 0 to 2, from 2 to 4, and so on. To get actual probabilities correctly within the margins that we have, we basically smoothen this or put the discrete data into a continuous probability distribution where you can then compute the actual exceedance probabilities. And what we're usually using for this kind of data, for wind data, is the Weibull distribution, as it's usually matching quite well observed wind data distributions that we see in reality. So we can see here that the blue staircases represent the actual frequencies of different wind speeds, and the red curve would be then the adjusted curve that we get for the Weibull distribution, right? And this is what we're taking then into account to compute finally the probabilities for the local wind speeds. So much to theory. I guess it's enough for now. I'm up for any question later to go into more detail, but I guess we go on at this point.
Cool. Thanks. Yeah, that's why Richard was here. So it's not that I don't understand necessarily, but what I have the customer kind of perspective in mind, right? So when I'm used to the setup, and then I press go, and then everything runs in parallel, and then this is where I get to. So although I care about what happens in the background, I don't necessarily need to know it, right? So thanks. There's actually a few questions. I think we'll cover them as we go. Yeah, I think we can cover them as we go. That would be interesting. Cool. Okay, so once the simulation is complete, and we will jump into the platform and look at this in a little bit of detail as well, you can basically start to get your wind comfort criteria results. So there's 3 results available right now, so Lawson, Davenport, and NEN. And they all look a little bit different. The standards are different, so the results will look slightly different. I think if I zoom in on the left-hand one, basically it's graded, right? So it goes from blue, and you can obviously read this and understand where it's comfortable to sit, and then it kind of works up from sitting to standing, walking into regions that are actually unsafe. So what we want to decide is, okay, for the most of our city or where our pedestrians are going to be, is it suitable for whatever they are going to be doing? So if we have, like, for example, a cafe, we really want to make sure we're in the A band where we have, frequent sitting is totally okay. If it's a pavement, the wind speed can be higher, right? So we can move up towards standing and walking. And this is a really quick way of basically putting together all of the information through all of the years and getting an idea of essentially how well the city performs, right? And then if we're going to change the design by adding a building or removing a building or whatever we happen to be doing, we can test that with SimScale before we really go too far down the design process and make sure that we know that the design is not going to cause problems for pedestrians. As you can see, and to talk to one of the questions too, some of the buildings here are curved, and one of the questions was, is it okay to have non-vertical building walls? You could essentially import anything you like, right? I don't think there's really a limit. So yeah, I mean, architects, from what I've seen, and a lot of my family are actually architects too, and they're crazy, right? They are really kind of dreaming up the most beautiful structures. And so yeah, the solver doesn't definitely need to cope with and handle those, and it does. They're nice people, by the way, in my experience. Just very artistic. Okay, I think the other really cool thing to mention as well is that, if I go back one slide actually, although this is really powerful and ultimately the result that all of our users want to get, what I think is also really interesting is to say, okay, what is happening transiently, right? So the solver is running transiently and it's capturing flow as it moves, or wind as it moves through the city over time. If we do happen to find a problematic area, what's nice is to dig into all of the different directions and to try to understand why. And that's what I think this gives us. And it's different as well to a steady state analysis. So a steady state is essentially a point in time, or if we run this to infinity and summed all the results together, that kind of thing. But you can see that basically, yeah, exactly. If we take a look up here, nearly nothing is changing, right? So the results over time and over days are going to stay very much the same. But if we take a look, say, here, or especially down here, I mean, there's some crazy weird and organic patterns happening within the flow, and ultimately probably repetitive as well over time. It's often really important to identify that, because we might have these kind of gusts that we need to make sure that we're aware of. Okay. What you'll see as well is that, and this is also one of the questions, I've changed the scale a little bit here to really highlight the flow. So actually, I think in reality it went from 0 up to around 8 or 9 meters a second. I've made it 5, so we're really highlighting all of the red regions inside the city. That means that basically everything on the outside, the flow is way over my 5 limit, right? So everything on the outside is going to look pretty red. You don't have to set it that way, and I can show you as well in the platform what the reality really is. I changed the scale just to make sure that we're highlighting what's happening inside. So basically the red regions are the highest flow regions, and the blue is where we have nearly 0.
Yeah, I think there was a question also from above for the wind comfort criteria, why these 3 that we saw differ so much in the results. Mm-hmm. So let's go once up. Sure. Exactly. All right, so these are particularly different wind comfort criteria. And for example, looking at the NAN criteria, for example, what we see here on the right side, right? So I think it's not really visible, but what it is based on is always the reference speed of 5 meters per second, right? And then the question is just how often is this 5 meters per second reference speed exceeded? And what this orange on the outskirts means here, that more than 20% of the time of the year, the velocities are exceeding 5 meters per second, right? But red is then here 15 meters per second. So you see almost no red here. It means that you will not exceed 15 meters per second for more than like 0.01 or 2. Then comparing here to the red on the left side for Lawson, this is completely a different threshold. So for this, what stays constant for all the categories is the 2% threshold, and the velocity varies. So here red means that we're exceeding 7.4 meters per second for more than 2% of the time, right? If our windrows has wind speeds that go up to maybe whatever 8 meters per second, right? Then we might hit this quite often, right? Almost all the time, but we'll never hit this more than 15 meters per second for the year. So it's not red on the right side here. So I hope that this is explaining the question that we had, why it's red on the left side and not red on the right side. So the red and red doesn't mean the same thing. Also, as here on the NEN, this is basically a safety criterion. On the left side, on this Lawson that we plot here, it's all the comfort criteria. So we would have another one for safety here, but that's separate.
Cool. Thanks, Richard. Glad you're here, most definitely. Okay, so what I wanted to do next is to dig in a little bit more into the transient results. So basically we have what is essentially a cafe here, and you can see basically the people sitting outside. And although I'll look at the thermal comfort, the pedestrian comfort in a second, and what we could see is that most of this was actually dark blue, but there was some lighter kind of blue-green regions here. So maybe half of these people are comfortable, half of them not so much. So that's kind of an interesting thing, I think, to think or to understand and to dig in, and that's why I think it's nice to be able to see all of the transient data. And it's also really nice for us to be able to communicate outwards, or for potentially you to communicate with customers as well, to say, okay, look, these are the risky areas, and here is why. Okay, so with that in mind, I thought what we could do is a design change to understand, okay, if we change the design in that small area, would it really have an effect, on a kind of city scale? So what we did is just add essentially like a kind of bush or something on the top and something on the bottom. I mean, it could be a statue, fountain, anything that's going to hopefully break up the airflow. And then again, we use exactly the same setup in SimScale, and then we can compare the two designs side by side. So what is interesting, and the flow I think is coming from somewhere northeast, it would look like. So basically it's coming in this direction downwards. You can see at the top it's like 70 degrees. On the left hand side, it's still kind of flowing into where people are sitting. On the right hand side, it can't. It has to go around the outside. And actually the comfort criteria was a little bit different. Okay, what I'd like to do is really quickly just jump into SimScale itself and show you how it looks and how the setup is done. So this is SimScale, obviously in the same browser as the presentation that we've been using. We have all of the different criteria here on the left-hand side, and we can just quickly switch between them. So it's really quick and easy. I mean, I think a lot of our customers really are only interested in one criteria normally, depending on the global region that they're working within and the standard they're working to. But it's so easy to calculate for all of them. They're simply all available. What I'll do is quickly walk through the setup. So again, just those 3 steps. And then also looking at the transient results, because we can really look transiently and have a quick understanding. So we'll do that as well. So really quickly, once you have your geometry in SimScale, up here you can change your region of interest, right? So we can make it smaller, we can make it larger. Okay, you're pretty free to choose. Normally kind of basing it around the city is pretty sensible. We can change our north angle, so you can see the N here and it will kind of move around as I change the number. So that is helping to orientate the city correctly. versus wherever it exists on the planet. Then we would set up our wind conditions. So this is the wind rows that we have. You can import your data, and soon you'll be able to just simply type it in Google Maps behind, and it will give you the wind rows for that location. And again, down here you have your wind exposures and your different standards. So you would choose, whether each angle is a city or simply flat and open. And that really changes the inlet profile, as Richard just explained. The final step before you run is to set up where you wish to capture results from. So we set up two things here. One is the pedestrian level, so 1.5 meters above the ground. And that's within the disk that we're interested in. But then we also set up a roof terrace, and you can see that just down here. And still 1.5 meters above this terrace, we're going to be capturing, again, comfort criteria. And obviously this is high, and obviously it doesn't have any kind of safety obstruction on the outside. So obviously this is going to be a poor result, but it's an interesting way of just saying, hey, look, we can easily capture different heights. So if you did have terraces, balconies, you could simply just add them here, and SimScale will calculate all that for you. So going back to the statistical data, again, on the rooftop here, we can see as well that we always get the same results. And I think finally, before we jump back to the presentation, the nice thing is that because we're calculating all of the different directions, we can also look at the results for any of those directions. So for just the 0 degree, so the flow coming in just directly from the top, we can load it up and animate. And basically we'll then again see the flow moving through the city, and it will help us to do exactly what we want to do and understand what is good and what is bad, and what can we do better. And obviously it's all in 3D, so we can zoom in pretty close and get an understanding really in detail of what is happening in the smaller areas. Anything you wish to add?
Just looking at the video, can't speak.
This is the problem with simulation. My wife actually tells me all I do is just make pretty pictures, but actually there's really a lot of fact behind the pictures too, but we don't argue, so. Okay, so a couple of things I think just to wrap up, and then we have quite a number of questions as well we can also talk about. So we can also offset from terrain. So the same way that I picked the terrace before, it's also exactly the same process to pick a surface as a terrain, and SimScale will simply give you the same result with one click, and so you would get the criteria and also the velocity or pressure as it moves over the curved terrain.
I mean, probably we should have used this one as an example. It looks awesome.
It does look awesome. I know, it's very cool. Okay, so I think just some kind of key learnings and facts before we wrap up and then start tackling the questions, which I think Richard has spent 15 minutes understanding and is ready to answer all of them.
Wait.
Whoa. I think it's important to mention the runtimes generally are a few hours. So that's really radically different to, waiting or to doing it with a different type of solver or, using a wind tunnel. And it means you can make really quick design decisions early on in the design process. And that's what we really want to enable everyone to do, to get really quick insights into, if I make a change of this scale in this city, what is going to happen? And yeah, hopefully you can do that more than once in a day. So the idea, and these for me easily take way less than a day, something like 2 hours. Once it's done, we can very quickly say, okay, this is wrong, I'm going to make this change. Try it again and see what happens. So within a few hours, you can really quickly optimize your design. So thank you very much for listening. Feel free to ask us any other questions. We have something like 15, 20 questions. Feel free to type anything else in that comes to mind, anything else you wish to know about what we've spoken about so far today. The webinar is recorded and we'll make it available on YouTube probably tomorrow. So yeah, it's all recorded. Actually, all of our webinars that we've ever done, and you can really look at the evolution of SimScale over the 7 years. I think a lot of the old ones are still there. It's kind of interesting to see, but yeah, this one will definitely be on YouTube.